94%. That is how closely a beam of ordinary sunlight, the same light hitting your window right now, just matched a laser at the single hardest task in quantum physics: creating entangled photon pairs. A team from the Max Planck Institute for the Science of Light and the University of Ottawa published the result in the journal Optica, and it overturns an assumption physicists have carried for decades: that you need a laser's clean, coherent beam to pull off spontaneous parametric down conversion, the process that splits one photon into two linked ones. Sunlight is messy. It is spread across colors, angles, and timings a laser never has to deal with. And yet, funneled through the right piece of hardware, it produced entangled photons anyway. Here is what they actually built, and what it does and does not mean for the future of quantum technology. Start with the process itself, because the word entanglement gets thrown around loosely. Spontaneous parametric down conversion, or SPDC, works by firing a pump beam of light into a nonlinear crystal, a material whose structure occasionally splits one incoming photon into two outgoing photons of lower energy. Those two new photons come out correlated in a specifically quantum way. Measuring one instantly tells you something about the other, no matter how far apart they later travel. That correlation is entanglement, and it is the raw resource behind quantum cryptography, quantum computing links, and proposed quantum internet infrastructure. For over 60 years, every SPDC demonstration used a laser as the pump. Because a laser delivers photons in a tight, coherent, single-direction beam, exactly the kind of input the nonlinear crystal was assumed to need to produce clean entangled pairs reliably. Consider what the team actually changed. Ordinary sunlight is incoherent. It arrives at a detector from a huge range of angles and contains a jumble of wavelengths and timings, the opposite of a laser's disciplined beam. To make it usable, the researchers built a cone-shaped solar concentrator that gathered sunlight and funneled it down to a narrow, highly polarized stream before it ever reached the nonlinear crystal. That concentrating step did not turn sunlight into a laser. It simply narrowed the mess enough for the down conversion process to still find entangled pairs. Inside it, the photon pairs that came out were then tested against Bell's inequality, a mathematical benchmark that only quantum entangled particles can violate. And the result violated it. Real quantum correlations, at 94% fidelity to a lab-grade laser source. That number is the headline for a reason. It means sunlight came startlingly close to matching purpose-built laser hardware most physicists assumed was mandatory. Consider what this unlocks beyond a curious lab result. Every existing quantum photonics setup, from quantum key distribution experiments to satellite-based quantum communication tests, depends on power-hungry, precisely stabilized laser sources that need dedicated electricity, cooling, and maintenance. A pump source that starts as ambient sunlight instead of a manufactured laser beam is, in principle, dramatically cheaper to run and easier to deploy somewhere without a power-hungry lab setup nearby. Satellites and remote ground stations being the obvious candidates. The research team frames this as evidence that natural, incoherent light sources are not fundamentally incompatible with quantum state generation, an assumption that shaped equipment design for 6 decades. That reframing matters more than any single number, because it opens an entire design space. Other incoherent or low-cost light sources that researchers previously ruled out without testing. Expect follow-up experiments trying to push the photon generation rate up before anyone treats this as practical hardware. Here is what the 94% number does not tell you. Fidelity measures how quantum the entangled pairs are. not how many of them you get. Sunlight is dramatically dimmer and less concentrated than a laser even after solar concentration. So the actual rate of usable entangled photon pairs produced per second is far lower than a laser-based setup delivers. And the paper itself frames this as a proof of concept, not a working replacement for laser sources. Nothing here demonstrates a working quantum computer, a quantum internet link, or any deployed technology. This is a laboratory demonstration that the physics works at all with an uncontrolled light source. Weather, time of day, and geographic location all affect how much usable sunlight is available. Constraints a laser never has to worry about. Treat this as a genuine physics milestone about what is possible, not evidence that sunlight-powered quantum devices are coming soon. Quick recap. Researchers at the Max Planck Institute for the Science of Light in the University of Ottawa used a solar concentrator to feed ordinary sunlight into a nonlinear crystal, producing entangled photon pairs that violated Bell's inequality at 94% fidelity to a laser source. Published in Optica. So, signal or noise? Signal. On the physics. This is a real, rigorously tested result that overturns a decades-old assumption that lasers are mandatory for generating quantum entanglement. And it opens a genuine new research direction toward lower energy, more sustainable photonic quantum hardware. Noise. On any framing that suggests sunlight-powered quantum computers or a quantum internet are close. This is a low photon rate laboratory proof of concept, not deployable technology, and the gap between confirming the physics and building a usable device is still large. Watch for follow-up papers chasing higher pair generation rates. That is the number that decides whether this becomes real infrastructure or stays an elegant demonstration. Subscribe for the physics headlines checked against the actual paper. Signal from the noise. Every week.